The second criterion for convergence of a series that we're going to see in this module is a so-called root test, and we're going to see that it's very similar in spirit to the ratio test. In other words, it's a way to compare the asymptotic behavior of your series, or more specifically of the general term of your series, with geometric series or geometric sequence. So let's start with looking at an example where we want to decide whether a series is convergent, and the sequence of general term is defined by n over 2 to the n when n is odd and 1 over 2 to the n when n is even. So we could try to use the ratio test, and in that case, of course, we have to distinguish the case where n is odd and the case where n is even in calculating an expression for the ratio an plus 1 over an. When n is odd, n plus 1 is even, and therefore an plus 1 is 1 over 2 to the n plus 1. N is odd, so an is n over 2 to the n, so the reciprocal is 2 to the n over n. When n is even, n plus 1 is odd, and therefore an plus 1 is n plus 1 over 2 to the n plus 1, and the reciprocal of an is 2 to the n, because n is even. So that means that if we look at the limit as n goes to infinity, when n is odd, here 2 to the n over 2 to the n plus 1 is really just 1/2, and we multiply that by 1 over n, so we end up with 1 over 2n for the expression when n is odd. And when n is even, we have 2 to the n over 2 to the n plus 1, that's 1/2, multiplied by n plus 1, so we get n plus 1 over 2. If we look at the asymptotic behavior, when n is odd, n goes to infinity, we have a ratio that goes to 0, and when n is even and goes to infinity, we have a ratio that goes to infinity. So if we look at the sequence of ratios an plus 1 over an, we have a subsequence that goes to 0 and a subsequence that goes to infinity, and therefore the sequence itself does not converge, does not even go to infinity. But that means that the ratio test does not apply, because to apply the ratio test, we need to have, for that ratio, we need to have either a finite limit or going to positive infinity. So here it's not converging in that sense, so the ratio test simply does not apply. So what can we do? Well, we could conclude with what we already have by using the ratio test not on this series, but something we can compare it with. Specifically, we could observe that an here takes a value either 1 over 2n or n over 2n, and therefore it's always bounded above by n over 2n. And then we can try to decide whether the series of general term n over 2n converges. And for that one, the ratio test is helpful, because if I take the quotient of two consecutive terms, I get n plus 1 over 2 to the n plus 1, multiplied by the reciprocal of the term for n, which is 2 to the n over n. 2 to the n over 2 to the n plus 1 simplifies with just a 2 at the bottom. And then I multiply this 1/2 by n plus 1 over n, which has a limit of 1, therefore the limit of the ratio of two consecutive terms for the series of general term n over 2 to the n is 1/2, which is less than 1. So by the ratio test, that series of general term n over 2 to the n is convergent. And by comparison, the series with smaller terms, the series of an, is also convergent. However, we would like a more direct criterion, and that applies to this series, and that essentially compares our series with 1 over 2 to the n without having to do this combination of tests, having to use a ratio test on something else and then compare. So we want something that applies directly to our series, and the idea is, well, we have this comparison that at the end shows convergence like 1 over 2 to the n. So we're going to try another way to compare with a geometric series. Right? One way was to look at an plus 1 over an, and if this asymptotically goes to a value that is less than 1, let's say r less than 1, then we can compare with a geometric series of r to the n which is convergent. Here we're going to look at the nth root to compare if the nth root goes to a value less than 1, then that means the general term will be bounded above by a power of that constant, and this way we should be able to compare with a geometric series. So let's look at what would happen if we look at the nth root of the absolute value of an in this particular case. If I take the nth root of an when n is odd, I end up with the nth root of n over 2, because nth root of 2 to the n is 2. And when n is even, I just get 1/2. If we're looking at the asymptotic behavior, we want to look at the limit as n goes to infinity, and in particular we're going to need the limit of the nth root of n. It's really n to the 1/2, which I can write e to the 1 over n ln of n, and the limit of ln of n over n as n goes to infinity is the same as the limit as x goes to infinity of ln of x over x. It's an indeterminate form of the type infinity over infinity, so we can use the rule of de L'Hopital. And that tells us that the limit is the same as the limit of the quotient of the derivatives. Derivative of ln of x is 1 over x, derivative of x is 1, and as x goes to infinity, that means that the top goes to 0, and the bottom is a constant 1, so the limit is 0. And that means that root of the nth root of n can be written as e to the something going to 0, and so its limit is e to the 0, which is 1. And so that means that the nth root of n over 2 goes to 1/2. So now we have both subsequences, when n is odd or when n is even, have the same limit 1/2, and therefore this nth root of absolute value of an has limit 1/2. So how do we use that to compare with a geometric series? So this is this type of result that we want to use. So let's look at the abstract setting where we have the nth root of the general term that has a limit equal to L less than 1. That means we can pick a number that is strictly between L and 1, and because the limit of the nth root of an is L, that means for indices large enough, we can make this nth root of an less than or equal to r, but that rephrases as absolute value of an is bounded above by r to the n. And the series of r to the n is a convergent geometric series, and we can get it started for the value of n that makes this inequality true. And so by comparison, the series of the absolute value of an starting at capital N is convergent, and therefore when we add finitely many terms, starting for instance at n, the series of absolute value of an converges, which means that the series an is absolutely convergent. Now what if the limit of this nth root of an is actually greater than 1? Well, then we can pick a number between 1 and L, and make sure that for indices large enough, the nth root of absolute value of an is greater than r. That means that absolute value of an is greater than r to the n, but r to the n, if r is greater than 1, is going to diverge to infinity. And therefore, the sequence an is going to be divergent because the sequence of absolute value of an goes to infinity. And that means that by the nth term test, since the sequence of general term does not go to 0, the series is divergent. So that gives us the root test, which is an alternative way of comparing our series with a geometric series. Instead of comparing by looking at the limit of the ratio absolute value of an plus 1 over an, we look at the limit of the nth root of absolute value of an. But at the end, we use the same kind of conclusion comparing with a geometric series. So we have the same sort of statements, specifically that if that limit is strictly less than 1, then we have absolute convergence. If this limit is greater than 1 or infinity, then we have a divergent series. And if this limit is exactly 1, then the test is inconclusive in the sense that we cannot decide if the series is convergent or divergent from that test, and you would have to go to another criterion. Just to show you that it's inconclusive, consider, again, just like in the case of the ratio test, the series of 1 over n which is divergent and the series of 1 over n squared which is convergent. When you look at the nth root of the general term for 1 over n, you get 1 over n to the 1 over n. And we just have seen that n to the 1 over n goes to 1 because it is exponential of ln of n over n, and ln of n over n goes to 0. The case of 1 over n squared, you get 1 over n to the 2 over n, and that's e to the 2 over n ln of n, and that has exactly the same limit. Ln of n over n goes to 0, so 2 ln of n over n goes to 0, and so the limit is e to the 0, which is 1. So again, we get 1 for the limit of the nth root of the general term. So what does that mean? That means that we have two series whose general term have the nth root of the for which the nth root of the general term has limit 1. One is convergent, the other one is divergent. In other words, this limit cannot help us decide for convergence. So going back to our example, we had seen that the limit of the nth root of the general term was 1/2, which is less than 1. So by the root test, this series is convergent. In that case, we can conclude directly by applying our criterion without having to combine different criteria. Turning to different examples, here you have 3 examples of the typical cases where you would use a root test. It's typical because the general term is the nth power of something else. And in that case, of course, it is easy to calculate the expression for the nth root. So this is the most common setting to apply the root test. So if I take the nth root of the general term in the first example, what I get is what is under the power n, specifically 4n plus 1 over 5n plus 3. And what we're interested in is the limit of this when n goes to infinity. In this case, I have a quotient of 2 polynomials of degree 1 in n, so the limit is the quotient of the leading coefficients, 4/5, which is less than 1. So we can conclude by the root test that this series is convergent. In the second case, again, the nth root of the absolute value of an is simply what we have under the power n, so that's 2n squared plus 1 over n squared plus 3. Again, quotient of 2 polynomials of the same degree. The limit is the quotient of the leading coefficients, 2 over 1. So the limit is 2, which is greater than 1, and that means that by the root test we can conclude that this series is divergent. For the third example, we have an alternating series, but we can conclude about the absolute convergence using the root test. As you have seen, the root test is a criterion of absolute convergence. If I look at the nth root of the absolute value of an, then I can drop the negative 1 to the n. I get 1 over absolute value of arctangent n, which is really just arctangent n, because arctangent is positive for positive values of x. And so, because the limit of the arctangent function at positive infinity is pi over 2, the limit as n goes to infinity of the reciprocal of arctangent n is the reciprocal of pi over 2, 2 over pi. And pi is greater than 2, therefore 2 over pi is less than 1. And therefore, by the root test, we can conclude that our series is absolutely convergent. Now it's time for you to turn to homework to train a little bit with both the ratio test and the root test.